Good morning, Dr. Wu and fellow classmates. Today we will present our project, Machine Learning Investor Personal Credit Score Classification and Risk Prediction. Let me start with the problem. Financial institutions have long relied on manual review to classify customers into credit score categories. This approach is time-consuming, products inconsistent results due to subjective judgment, cannot scale to handle large volumes of applications. Our project has three objects: reduced feature data science, combined with comprehensive data quality assessment and binding risk rank analysis. Our dataset comes from Kendall's credit score classification, containing 100,000 records with 28 features and one target variable. The features span 4 categories: identifiers, demographics, financial indicators, and behavioral risk features. The target distribution is imbalanced. Standard accounts for 53%, poor for 29%, and good for only 13%. As you can see from the bar chart on the right, the raw dataset has significant missing values with monthly in-hand salary at 15% and type of law at over 11%. We also found special character contamination like underscores appended to numbers. Explore, model, and interpret. In data cleaning, we use the regex to detect and remove special characters, converted month names to integers for chronological sorting, and replaced invalid placeholders with NaN. For outline and treatment, we grouped data by customer ID and computed the IQR between the 40th and 60th percentiles. Special characters were stripped from numeric congruence. Evaluated placeholders in SSN, occupation, and payment behavior when replaced and failed. Extreme outlines in bank accounts, interest rates, and age were captured using coastal IQR and then re-imputed with the group median. The credit history age string was passed into a numeric total month feature. After it confirms that these numerical features have statistically significant differences across credit score categories, the pair point shows the relationship between annual income, outstanding debt, and monthly investment. We can see that lower income groups tend to have concentrated debt. These findings guided our modeling. Class imbalance requires macro F1 and ROC AUC beyond accuracy. Strongly correlated features must be retained, and the intercorrelated income values are candidates for future reduction. Analysis. Before modeling, we conducted a binding analysis to see whether converting continuous variables into discrete groups could simplify patterns. The chart shows the risk rank comparison for each bind variable. We test both in-call interval and in-call frequency approaches. Our final strategy uses in-call interval binding for average income with 5 binds and equal frequency binding for credit history age, monthly balance, interest rate, relay from due date, and the number of delayed payments. Binding products inotonic risk ranking. As the bin index increases, credit risk changes consistently in one direction. However, it was nothing that finding slightly reduced model accuracy by about 1 percentage point because it discards some useful numerical granulation, though it improves the interpretability. Slide 9, model selection. We compared 3 models. Logistic regression as a linear baseline is coefficients provide direct interpretability. Random forest or bending ensemble that captures non-linear relationships through multiple decision trees and is insensitive to feature scanning, and XGBoost, a gradient boosting method that builds weak learners sequentially for strong generalization. Each model was treated on 4 data categorizations: row scanned, bind scanned, row unscanned, and a reduced set with only the top 10 features. Slide 10, main results. The main results table shows our key metrics. On a full RAM scanned dataset, random forest achieved the highest test accuracy at 81.17% and ROCA UC at 0.9129. XGBoost reached 77.40% accuracy and 0.8838 AUC. Logistic regression achieved 65.99%. The 3 confusing matrices provide a class-level view. Random forest on the left shows strong diagonal performance, but its 100% training accuracy indicates several overfitting. XGBoost in the center has a much smaller train that has better generalization. Logistic regression on the right is stable but limited by its linear boundary. Notice that all three models perform best on the standard class, which is a majority. The good class is the handiest to predict because its smallest minor rating at only 18%. The tables on the left show how potential choices affected performance. Binding reduced 3 module accuracy by 1 to 1.5 points. Simplification came at a cost. Scaling had a dramatic 5.45 percentage point impact on logistic regression, but was negligible for 3 models, which is still radically expected. Feature reduction slightly decreases random forest accuracy, but substantially reduced the overfitting from 100% to 89% for XGBoost. Removing rig features actually improved the test accuracy to 77.72%. The ROC curve compressed visual on the right confirms that both random forest and XGBoost maintain strong discrimination ability across the full and reduced feature size. The right panel discusses that business implications of misclassification, which is critical in a credit scoring context. If a poor risk customer is incorrectly classified as good or standard, the latter may approve a risking law, leading to potential default and financial loss. Conversely, if a good customer is misclassified as poor, they are unfairly denied credit, resulting in lost revenue. Therefore, the best model should be selected for class is essential for effective risk management and interpretability matters for business decision making and regulatory compliance. Slide 30. Key predictive features. XGBoost feature importance chart shows which variables contribute most to credit score prediction. The cornerstones across all 3 models identifies interest rate, change the credit limit, number of credit cards, delay from due date, outstanding debt, and credit mix as the top predictors. These features capture borrowing cost, credit exposure, repayment discipline, and debt border. Key takeaways: ensemble methods significantly outperform linear baselines. Our quartile-based cleaning strategy proved effective. Scaling matters only for linear models, and credit behavioral features dominate prediction. This concludes